Okie dokie, good morning. Test is still happening on Thursday. No, yeah, it is. Test will be here. Test will start at 8 a.m. Test will end promptly at 9:15. It's going to be the same gig as we did before. I'm writing the test so that a normal student can do it in an hour, 5 minutes, and then we're going to have a 10-minute buffer. If you are an SDS student, please meet me outside my office at about 7:50. What's going to happen is I'll introduce you to your proctor, and then we'll kick that off like last time. If you are SDS student and you just got your form, come see me and present it to me, and then I'll assist you with the information about the test. In terms of my view of things, I thought that the first test went well for what it was meant to do, which was introduce you to a first test, since probably none of you, or if any, a very small number of you have ever taken a physics test before. So the second test, now that we're all veterans in taking physics tests, we're going to push boundaries a little bit. In the second test, we have covered way more material, and it's going to build on what we covered in the first test. So it's going to be a little bit harder, but then again, you have a little bit more experience on how to deal with those things. So it's kind of balancing out. Here, ignore what the test says. It is actually a test too. Last Friday, or definitely over the weekend, because it's on Blackboard right now, I posted all of the something called a Test 2 pack. And the Test 2 pack has a whole bunch of tests. What I'm going to do probably today is I'm going to do this one right now for today, and then later this afternoon, if you want to come to that lecture, I'm going to do these two tests come from the summer of this year and last year. So the 2015 test and the 2016 test. They're pretty much the same. So let's get to it. Once again, I want to stress not caught as in caught cheating, but I definitely caught individuals not following the rules. And the biggest rule that was not never obeyed, but a large portion of people didn't quite understand this rule and this rule. I will not mark answers correctly for those that are put on the paper, on the test. You gotta put it on the Scantron. Would the MCAT care if you put the right tests on the physical copy? No. So neither will we. The other thing is that if you put the answers on the test itself, it won't count. As an example, this is the right-hand rule, which is the appetizer. There were people who put the answers there. And then there were people who put the answers down here. Those answers will not count. Please put your answers on written section, and then as a word of advice, we're a little bit more understanding with this, but please understand it. Do not write in the upper left-hand corner of a front page, and do not write in the upper right-hand corner of a back page. And why is that? That's where the staple goes. And a lot of people, what they do is they put the appetizer for the right-hand rule right in the upper left-hand corner and then staple it, and then my graders have to pry that thing apart, and then they get upset. And an upset grader is an unwanted grader, because upset graders, they just let that red ink fly so they feel better about themselves. So don't do that. All right, so let's do this. Standard format, 25 multiple choice, 2 points each. One conversion, one appetizer, and then 3 problems for the same point spread. As you can see here, lots of equations and stuff that you'll need. Not all will be needed, and none of them are identified. So what I'm going to do also is I'm going to go through this and I'm going to kind of proof it, as well as proof the multiple choice and make sure that it looks a lot better and there's less probability of an incorrect multiple choice. So first question. Thread is being, let me blow that up. Thread is being pulled off the spool. The spool revolves at a constant rate. Which of the following is false? Is omega constant? For thread being pulled off a spool at a constant rate? Yes. V is omega R. If V doesn't change, and obviously R isn't going to change, omega has to remain constant. Is V of the edge greater than 0? Is the velocity at the edge of the spool greater than 0? It's moving, so obviously that's true. Is alpha 0? Yes. Why is alpha 0? Omega is constant. What's the relationship between alpha and omega? What? What's no? What is the equation that contains both alpha and omega? If you're going to change alpha to omega, what do you do? Or what if you've got omega? If you got a function of omega, how do you get alpha from it? Yes, but as a raw, I'm looking for more of a definition. Alpha equals exactly. Alpha is the change of omega with respect to time. And once again, I'll say this. I'd much rather have you say immediately, alpha is the change in elephant. Say it with conviction, say it quickly. This whole alpha is the change in with respect to, no, that's not allowed. I don't care if you're right. Don't say it with ambiguity. Is omega non-zero? 48 hours before, and I'm hearing crickets. This is going to be fun. Yes, it's non-zero. So that only means AR is what? Is that true? AR is 0? No. How do you know it? Well, all the others were right. What else do you know? What is A sub R? It's not angular acceleration. It's radial acceleration. What is A sub R as an equation? V squared over R. Yeah. V is non-zero. Why? Because spool's coming off the thread, or thread's coming off the spool. And R is constant, so AR has to be non-zero. So it is, answer's E. You're running around the circle. You run faster. What doesn't change? So you're running faster. Does your radial acceleration change? Yes. AR is V squared over R. V changes, so AR changes. Does your angular momentum change? Yes. It's because angular velocity changes because you're going faster around the circle. Does your kinetic energy change? Yes. What is kinetic energy? 1/2 mv squared. V changes, so kinetic energy changes, which leaves only moment of inertia. Now you could treat yourself as a point particle when you're running around the circle and you run faster, What changes in the moment of inertia equation? Nothing. It's a function of mass. I mean, if someone threw a cheeseburger at you and you ate it, yes, your moment of inertia would change. If you ran further outward from the edge of the circle or closer inward, your radius would change and your moment of inertia would change. But neither of those were mentioned, so that doesn't change. Inelastic collisions conserve only momentum. Now, when I mean energy, energy as a local definition for this test and in the class is mechanical energy. Since we haven't introduced the concept of thermodynamics and the conservation of energy for the whole universe, we're only really concerned about energy of systems or mechanical energy. So mechanical energy is not conserved in an inelastic collision. What does conserve energy? Elastic collisions. Are elastic collisions common or rare? Rare. This is a good question. I just thought of this. Does an elastic collision produce sound? No. What is required to produce sound? Energy. So if sound is produced from an elastic collision, it would have less energy, which would be a paradox because you can't release energy in an elastic collision. So no sound. Ooh, that's a good question. I may add that if I have the time to remember. An Atwood's machine has no friction. What is the ratio of E start over E end? It's 1. If there is no friction, the energy at the beginning is the energy at the end. Divide both sides by E end and then you get 1. Now, it was asked of me earlier this week, what equations do you want me to memorize? And my response was, you don't have to memorize anything new, just remember the things that you should remember from when you were 5 years old. Well, not 5. When did you learn about circumference? 5th grade, 8th grade, 10th grade? Somewhere between 6 and 8, which is definitely before college. So you should know what a circumference is. And a circumference is what? 2 pi r. A circle rotates 3 times in 6 seconds. What is the period? This is one where there's a typo. And I think what I told the class is 3 on the test is actually equal to 2. So that's how I changed it. And they were like, what? And then I was like, okay, fine. So it's either 2 hertz, 2 seconds, 2 meters, 0.5 seconds, or 0.5 hertz. It would be B for 2 seconds. Momentum is the product of what 2 quantities? Momentum is the product of what 2 quantities? Mass and velocity. You're not endearing me. Like, it's kind of making me go, well, fine, I'm going to write a hard test. It's not like they know it anyway. All right. A ball makes 3 revolutions. How many revolutions did it rotate in radians? 6 pi. 1 rotation is how many radians? 2 pi. So that's another thing that I expect you to know. Circumference and the arc in radians for 1 rotation. Sum of the torques equals I alpha. If the sum of the torque, or if it was in rotational equilibrium, what would the sum of the torques equal? 0. So know the difference between equilibrium sum of the torques and non-equilibrium sum of the torques. The unit for period is what? What? Second. What is that?
Goldfish.
Goldfish? Okay, very nice.
Rainbow goldfish.
Rainbow goldfish. Are they different flavors for the goldfish? Okay.
They just taste good.
What? My guess is no, but I think it would be a valid thing to have T equals F inverse. I could say that velocity is circumference over period and distance over time. I think those would be two valid equations to give. I'm also looking at 2 pi n is equal to theta. Units of radial acceleration, a sub r, are meters per second squared, yes. Units of angular acceleration are so this something I would accept either radians per second or blank per second. Yeah. So it could be this. It could be, I'd be happy with this. I'd also be happy with that. Either one of the three. An object in object in translational equilibrium means what? Sum of the forces is equal to 0. You are running around the circle like the first time, and you still run faster. What changes? Oh, it would help if I showed the question. E, angular momentum. Because, well, unless you say the puppies just get cuter, and then you would be like, okay. Yeah. Which law is Hooke's law in vector notation? E. Let's go over this. Ignore the F for this part. What is this? It's mass times radial acceleration. What's R cross F? Sometimes I would even say D cross F. That's torque in vector form. B is what? And it is written correctly, force, or Newton's blank, what? Second law, not first. The first law is object in motion stays in motion unless you F with it, and etc. Circle rotates 8 times in 4 seconds. What is the frequency? 0.5 hertz. What does Hooke's law say? Hooke's law, not Hooke's law. Look in the lecture where I talked about springs and the potential energy of springs. If you take a object and displace it, then the force on the object is in the opposite direction, and there's a factor of K. K is the spring constant. If I'm looking for magnitude only, which is typically how I deal with things, F is equal to kx, where x is the distance. Second is the unit for period. What is the unit for frequency? Hertz. What is the unit for energy? Joules. What's another way of saying joule? Newton meter. What's another way of saying Newton meter? Kilograms meters squared over seconds squared. And what's really interesting when you think about it, it took Einstein to come up with E equals mc squared. E is in joules, m is in kilograms, c squared, velocity of light squared, meters squared, seconds squared. So the units check. So if you ever wanted a quick way of figuring out, well, what are the energy of units? Everybody knows E equals mc squared. So you need to slap that together. Units of coefficient of friction. None. Yes?
On number 16, why would it be 2? If there was 1 over 25.
So who said, someone here said 0.5. You said 0.5 hertz, correct? All right. One of the yieldings has challenged you to open intellectual combat.
Okay.
So feel free to stay out of this. I'm going to go hurt her in just a minute.
Oh, it is, she's right.
She's right. Tell me what you did wrong.
I did period.
You did period. So period is the total time over the number of oscillations. So frequency, which is the inverse of period, is number of rotations over total time. Fair enough. I'm not done with my coffee yet, so things are a little murky. Now would be a good time for me to write the test. Whatever, just throw them at him. Throw last year's at him. And those of you, I'll tip my hand just a little bit to tell you what I did on the first test. We went over all the 213 tests from last summer of this year and this spring, but I kind of was a little bit vague on presenting tests from last fall. Did anybody find the tests from last fall? No one? Oh well, I got away with that one. Because I basically took the problems from last fall and reprinted it. So I slid one by the class. Do I plan on doing that again? Well, no, I'm just telling you how I did it last time. So there was an individual who put together a book of every single test I gave for 5 years and just had it and was flipping through it and was reading the signs. And so there you go. Normal force is always blank to friction force. What is blank? Perpendicular. The reason why I'm still harping on normal force and how you get it is because normal force is related to friction force. Energy released is force times distance. And that force is the friction force, so you've got to pay attention to what the normal force is. You are walking on a disc that is spinning at a constant rate. You walk further away from the center. What changes? And so you're walking effectively on a line. So to you, you're just moving in a straight line. And then that disk is rotating. Is your angular acceleration changing? No. Why? It's not related to the radius, and also I said, what did I say in the first sentence?
So B is constant.
Hold on, I'm getting a lot of stuff right now. Let's deal with it one at a time. If the angular velocity, is that changing? No. Why? It's spinning at a constant rate. So we have eliminated that. Is angular acceleration changing? No. Why? Angular velocity is constant. Is the period changing? No, because it's spinning at a constant rate. If it's spinning at a constant rate, it could spin at 2 seconds per rotation. So regardless of your position on the disk, it's still going to spin at 2 seconds. So period doesn't change. Does frequency change? No. But let's talk about radial acceleration. As you're moving further out,
The R changes.
the R changes. And V is equal to omega R. So if R increases, V must increase.
Is it AR equals V squared over R?
Yes. And that let's deal with that for just a moment. If all I asked for is does it change? Answer yes. Radial acceleration changes. Here's a trick question. I wouldn't call it a trick. It would just say, are you, I think I asked this in the afternoon class, I know for sure. Does radial acceleration as you're moving outward on a disk that is rotating at a constant rate, does your radial acceleration increase or decrease? Okay, it increases. And what the student said at the time was said that it decreased. And I was like, well, why? And he goes, well, A sub R is V squared over R. And since R gets bigger, AR gets smaller. And I was like, what? And he didn't take into account that V changes as well. Well, what's V? Omega R. Substitute that in. Omega squared R squared over R. So AR is equal to omega squared R. So when R increases, omega is constant, AR must increase as well. Object is resting on a table. Which of the following is not zero? Normal force. Is the sum of the vertical forces non-zero? Is the sum of the vertical forces non-zero? No. How do you know this? It's not doing anything. It's so much of, you can get so much information out of, it's doing nothing. If it's not moving up or down, the sum of the forces is zero in the vertical. Is the sum of the torques zero? Yes. How do you know this? Not rotating. So by it not doing anything, it's not moving up, down, it's not rotating, and you're good to go. Life is good. Life is good. Not as good as no friction, because yay, no friction. What are the units of coefficient of friction? Blank. What are the units of angular momentum? E. Angular momentum is what by definition? What equation do you use? I omega. What is I? What are the units of I? What did you say?
Oh, 1/2 mass times velocity squared.
No. On several different layers.
Depends on what you use.
It depends on what you use. Just say, I asked for the units of moment of inertia. Give me the units, or no, give me the equation for a disk's moment of inertia. You got it right except for one letter. Anybody else? 1/2 mr squared, not v squared, r squared. So 1/2 mr squared, units of mass, kilograms. Units of radius, m squared. So the moments, yes, I know, just as funny. The units of moment of inertia are kilograms meters squared. What are the units of omega? Per second, or inverse seconds. So the units of moment of inertia, I'm sorry, angular, blah, blah, blah. Yeah. Why should it be? Oh, yeah, it is B. Not that. So I gave you several answers that got close, but not quite. Say that again.
I is kilograms meters squared.
Mm-hmm.
And then
Units of I is kilograms meters squared. Units of omega are inverse seconds. So I omega is kilograms meters squared inverse seconds, or B.
how do you like prove that the coefficient for friction is 0, like no units again?
How I would prove that, the definition of friction force is what? Friction force is equal to mu sub k times normal force. So mu sub k is friction force divided by the normal force. Friction force is expressed in newtons. Normal force is expressed in newtons, which leaves you with blank. So that's how I would prove that the coefficient of friction is unitless. Frequency is 2 hertz. Angular velocity is what? E. 1 hertz is 2 pi radians per second. And you can get this by saying 2 pi frequency is equal to omega. Trying to make sure this is going to be on. Whoop. Rotational mass is what? Moment of inertia. What? Rotational blank is angular velocity. What is blank? Rotational blank.
Can you move it up?
Well, no, I'm still doing 24. Rotational blank is angular velocity. It's kind of almost a trick question. Rotational velocity is angular velocity. Well, this is kind of dull. Rotational force is what? Torque. Good. Rotational force is torque, just like I say rotational mass is moment of inertia. Relationship between normal force and kinetic friction force is what? B. What I just covered over in the proof of the units of coefficient. All right, so those are the multiple choice. What I'm going to do later today is I'll go over all of the multiple choice for this test, because there are multiple versions. The version numbers for 2016 summer are written at the bottom of the right-hand rule. And if we can, no bonus points, but if you look at the first version is Mallory, second version Lana, third version Sterling. Who am I talking about? Archer. Very good. So I like to put some personality into the, and if you don't know who Archer is, I leave it to you as a homework assignment, and you've got to watch the first season by Thursday. What?
What about studying for the test?
That means I got to make an Archer test on Thursday. So, what we're going to do for the rest of class is we're going to go over the Mallory test. The only difference between the two tests are numbers.
Was that the multiple choice for the Mallory test?
Yes. So the multiple choice was Mallory.
So are you only gonna post the answers for Mallory and stuff?
Yeah, I'll post them for everything.
Okay.
What I'm going to do is I'm going to take that file, mark up the answers, and post that, and then you can see what it is.
What about the video?
The video? No, I'm going to keep it, and then in the middle of the night I'm going to delete it, and then cackle maniacally. So, and then what I'm going to do is I'm not going to release the video. I'm going to release the video of me deleting it, and then I'll send that to you. Yes, I will post everything. A cross E. C. C cross D. F. E cross C. A. A cross C.
L.
A cross C. F. All right, I was waiting for the E's to see the error of their ways. D cross F. C. Now what I do for the right-hand rule is I draw this sketch out, and then I place 3 sets of random letters, and then I just make up right-hand rule games. So the 3 versions of the right-hand rule will be fairly random. Problem 1. So given the disk below, determine the missing values that are listed in the box. So from this box, can I safely assume that alpha is 0? No. How do I know this? Because there's a force blatantly there on the disk.
You're asking for alpha, so
What?
you're asking for alpha, so you wouldn't want us to just write 0. You'd want us to solve.
Oh, I'd want you to solve for it, because if you saw this and you wrote alpha is equal to 0, the red pins are going to come out quick. When I look at this, I would be shocked if alpha was 0 in this, because there's one force on a mass, that thing's spinning up. So N is equal to 300, the number of rotations. The mass of the disk is 1200. R is equal to 2. T, curiously enough, is 100 times the square root of pi seconds. That's almost as if I sat down and did it before the test and figured out what numbers to use. In the back.
For the right angle game, how did we get C for number 1?
All right, for C, or I'm sorry, for number 1, A is towards the audience or towards the back of the room. E is towards the ceiling. That means it points to that wall over there, which on the paper is C. Do you see that? Who raised their hand? Did you understand that? Not okay. A is towards you.
Oh, A is up.
Or, yeah, towards you.
No.
Out of the page.
Okay.
Did I just go insane? A is out of the page, right? Okay.
That's your finger.
If you
Yeah.
have like this, and you just do this, and you use that, you get C.
It's C in however this thing is aligned. A is out of the page or out of the board. E is towards the ceiling. C is that way. So that works. Now if I had it like this, do I get the same answer? You do, yes. A cross E. A is still out of the page. E is that way. Thumb points down. It's C again. The problem comes from when you're looking at the page on the board and looking at the page on your test. If you're constantly flipping between those frames of reference, you're going to get confused. You're going to get swapped around. So if you're going to use the board, always use the board. If you're going to use the page on your desk, always use the page on your desk.
What does it say for T equals, is it 100 square root of pi?
Yes. And like I was saying, it's almost as if the professor was doing the problem and needed to like have a pi to cancel out. So I just made the time like that. If you see something like that, the professor is basically screaming at you, I've done these problems. The numbers are going to be working out rather well. The initial omega is 0. The force on this thing is 300 newtons. Now, I will say this as a, not as a warning, just letting you know. It won't be a simple disc. It will be a disc with a stick, disc with points, or the disc will have like a stick that's like this. So be ready to add moments of inertia and be ready for one of the particles to need the parallel axis theorem to calculate the moment of inertia.
So if it needs parallel axis theorem, you just add for that certain.
It depends on the geometry. If it's just a point, you add an mr squared. If it's a bar lying directly across, you add a 1/12 ml squared. I haven't decided what the geometry is going to be. It may be...
What is this? This is not an example of that?
No, it's, well... Oh, it is. I'm sorry. Excuse me. Bad, professor. There is a stick lying across. Excellent. So we can do something like this. Will I need parallel axis theorem in this? No. If the stick was off center of its center of mass, then yes. But in this case, no. I need to know the mass of the stick and alpha. Now for something like this, you got to get the usual suspects out for the problem. Sum of the torques is equal to I alpha. Torque is the force times whatever distance that force is from the center of rotation. Theta equals theta naught plus omega naught t plus 1/2 alpha t squared. The theta is 2 pi n. Let's see, what other fun toys do I need? The total moment of inertia is the moment of inertia of the disk plus the moment of inertia of a stick. And in both cases, they're rotating about their center of mass. So both are rotating about their center of mass. Neither will need the parallel axis theorem. The moment of inertia of a disk is 1/2 mr squared. The moment of inertia of a disk is 1/12. That's mass of the disk. That's mass of the stick. L squared. What's the relationship between L and R? This stick is running from edge to edge on the disk, passing through the radius, or passing through the center. So what is the length of the stick? 2r. So this becomes 1/12 m sub d r squared plus 1/12 ms 4r squared. 4 over 12 is 1/3. And you know what? In this particular case, I'm looking at what I'm going to need to do. I'm going to keep it like this. Mm-hmm. Because it's lying directly across the disk. So I'm going from there to there. There to there is 1r. There to there is 2r. So the length of the stick is 2 times r. And then you square it, and that's where the 4 comes from. And there you go. It's 1/3. Did I give the radius? No, 2 meters. Okay, fine. We can plug and chug. Yeah, I'm thinking the problem is that mass of the disk and mass of the stick are a little bit different. So this is md2 squared plus 1/3 ms2 squared. This makes the total moment of inertia simplified to mass of the disk plus 4/3 mass of the stick. And that's the moment of inertia. And just as advice about how these problems are going to work, they are going to be of such a flavor so that the people who do things algebraically will be an advantage over the plug and chuggers. There will be things in these problems which will need algebraic manipulation. So that's the moment of inertia. Let's attack theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Theta naught always 0. Omega naught is 0. Why? Because I said so. And then I give you n, so 2 pi n is equal to 1/2 alpha t squared. Well, you just can't hold on to anything right now.
My homework says that you're not meant to keep up on picking it up.
Okay. So, do I have n? Yes. Do I have alpha? No, I'm looking for alpha. Do I have t? Yes. So what I'm going to look for is alpha. So 4 pi n over alpha, or no, not alpha, t squared is equal to alpha. That's what I'm initially looking for. Had there been another unknown, I would have gone the other route and attacked the other problem. 4 pi times 300. Now, t is 100 times square root of pi. So t squared is 10,000 pi. And the pi's cancel. 4 times 300, 1,200. Divided by 10,000. 2 of the pi's cancel, or 2 of the zeros cancel, numerator and denominator. And I'm getting an alpha of 0.12 exact. So the whole idea of 10 times or 100 times the square root of pi was totally intentional. What I do is I practice writing problems. Trust me, on the test, you may bring pens, pencils, erasers, colored pens, highlighters. Love highlighters. You can bring a ruler. Rulers will not be provided if you don't bring one, and bring a calculator. I keep taunting my class with one day I will ban calculators in tests. But that would only be because in this type of problem, do you need one? No. It's a totally legitimate problem without a calculator. So it would put a burden on me, which I gladly accept, to write problems where you don't need it. And occasionally one slips in. I have alpha. Sum of the torques is 1 torque, which is force times the distance, which is equal to I alpha. Force times distance divided by alpha is equal to I. The force is 300. That distance is 2. The alpha is 0.12. So 600 divided by 0.12, 5,000 exact. Now I have the moment of inertia. The moment of inertia is 5,000, and it is equal to 2 times the mass of the disk plus 4/3 the mass of the stick. Now there's a r square, or a meter squared in the units running around, so even though this does look like a mass addition, it is moment of inertia. I minus 2 mass of the disk is equal to 4/3 ms, so 3/4 I minus 2 md is mass of the stick. So 3/4 5,000 minus 2 times 1,200. 2 times 1,200 is 2,400. 5,000 minus 2,400 is 2,600. 2,600 times 3 divided by 4. Oops, not that. 2,600 times 3 divided by 4 is 1950 kilograms. Exact. I think a valid question on the test, if I say it, then it's definitely accepted. A good question would be, are the numbers nice? Are they going to turn out nice? And I would say, if the answers were like this, the answer would be yes. The answers are going to be turning very nice. So if you do this physics problem and then you just start rolling out whole numbers for the answers of everything, or very nice 2 sig decimal answers, then you're in the right direction. All right, so that's problem 1. Problem 2, Atwood's machine.
You have to like memorize what formula you start with, like, for those problems?
I would probably take this and roll out of the gate with that, and this. And I think that, and a basic knowledge of the moments of inertia. So, the moments of inertia, yes, will be on the test. It will be one of 3 geometric shapes: point, stick, disc. Those 3 will be on it, as well as the equation for parallel axis theorem. Now, how you identify and use them, that's your concern.
Is that already on this, old?
It should be. Hold on, let me take a look.
I center mass with MD squared.
Yeah, is it written? Yeah, it should be. Otherwise, I'll definitely make a check. There, and there. Third line. All 4 equations that I mentioned.
What is IT is?
I sub t is total. I sub cm, center of mass. Now, sometimes I'd either write IT or I prime, or sometimes I've even used I. But if you see ICM plus MD squared, that's a parallel axis theorem. It doesn't matter what's before it.
And that's if the stick is poking like out of this circle.
If the stick is rotating around its middle, then it's fine. Okay. For Atwood's machine, this is an Atwood's machine with energy. The initial velocity is 0, so energy initial is just the potential energy initial, and the Atwood's machine will be on a flat surface up here and then straight down over there. So because of that, the potential energy is m sub 2 GL. Now, there is friction, boo friction. That energy removed is frictional force times the distance. The friction force on a flat surface is that. So this becomes mu sub k mgl. The distance that it fell, or the distance that it slid across, is the same as the distance that it fell for mass 2. The other thing is that you need to remember that all of these masses here is the mass on the surface, or m1. The last thing, the energy final, is 1/2 m1 plus m2 v squared. That is the total mass. The energy final is only kinetic energy. Since both are moving, and they're both moving at the same speed, you can write kinetic energy like this. So 1/2 m1 plus m2 v squared. In many of these problems, I ask for the final velocity. In this particular problem, velocity was given, and you have to look for length. So length is m2 minus mu sub k m1. And that is equal to 1/2 m1 plus m2 v squared. I'm looking for L. So L is this. So M1, 5, M2, 25, V, 60. 2 times 10. Gravity in 213 will always be 10. It's easier to divide stuff out. M2, 25 minus 0.2 times M1, which is 5. So it is 30 times 60 squared divided by 20 times 24. 0.2 times 5 is 1. 25 minus 1 is 24. And that gives you, apparently, I was in a very good mood with numbers, 225 meters. Oops, excuse me. Even I dropped calculators. Okay. So that is the Atwood's machine problem. Just a simple arrangement of energy. You got to derive this. Once again, I will say this. You've got to derive this. If you magically go, poof, a miracle occurs, the grader will go, poof, there goes your grade. It's simple. Question? I would say it's almost identical in steps. What will not be identical is what I make unknown. Okay, last part. Oh, put that back up. Torque bar. Torque bar is, I'm looking for F1 and F2 of this thing. It has a 2 fulcrum set. And we get this. I'm looking for F1 and F2. And I'm being bad. I'm telling me, I'm really horrible. R1 is equal to 2R2. R2 is not given. R3 is 3 times R2. And R4 is 0.5 R2. Man, I was being a jerk that day. But what this is really saying is, if I didn't give you R2 and I specifically said it's not given, you probably won't need it. Also, it's to defeat the plug-in chuggers, because a lot of people freak out and go, I gotta have numbers and I didn't give you any. But what I did give you was a whole bunch of ratios. You know this thing isn't rotating. I'll call that point A. The sum of the torques about A are equal to 0. Picking A as a point effectively eliminates F1 from this equation. The distance from the force to the rotation point is 0. Torque is force times distance. Distance is 0. Torque is 0. I don't have to worry about it.
And that would be the same if you have made L2.
Yeah, it would be the same. If I chose that, then F2 would be eliminated. You've got to pick a rotation point so that one of the unknowns is eliminated. So 0 is equal to M1R1G, should be M1G times R, but it doesn't really matter. Second torque, M2GR2. That's the distance, that's the force. Third torque, F2, R2 plus R3. Fourth torque, M3G, R2 plus R3 plus R4. So these are the 4 portions. Use the right-hand rule to figure out sine. You always start at the rotation point and then move to the force. Distance R1 is to the left. The force M1G is down. Thumb goes out of the page. Positive. Now M2 and M3 are both to the right and both down. They're both negative. F2 is to the right, but F2 is up. Positive. So that determines the signs. We're looking for F2. So M2G R2 plus M3G R2 plus R3 plus R4. That comes over, that comes over, that comes over. And that is equal to F2 R2 plus R3. Now at this point in time, I would probably do a substitution.
The F2,
What happened to what?
when you were putting it in the equation, like after M3G, how come you didn't put F2 right there?
How come I didn't put F2 right here?
Go down to it.
This? Well, what I did is I moved that over, that became this. I moved that over, that became this. I moved that over, that became this, and then F2 went down along with it. This is one line. This is the next line.
Oh, okay.
I'm going to do a substitution. M2GR2, I'm keeping my R2s, plus M3G R2 plus 3R2 plus 0.5 R2 minus M1 R1 2R2 G equals F2 R2 plus 3R2. Yeah. Factor out R2s. So the R2s aren't needed numerically because they cancel out. Now, I'm going to factor out a G and add up. GM2 plus M3, 1 plus 3 plus 0.5, 4.5, minus 2M1 is equal to 4F2. So G over 4, M2 plus 4.5 M3 minus 2 M1 is equal to F2. 10 divided by 4, M2, 20, plus 4.5 M3, 60, minus 2 M1, 10 is equal to F2. Oh, that's kind of neat. Those go away. 675. And now, for the last part, sum of the forces vertically is equal to 0, which is equal to F1 plus F2 minus M1G minus M2G minus M3G. It's not going up or down. So M1 plus M2 plus M3G. All I did here was factor out a G and a -1 and then moved it over to the other side. Minus F2 is equal to F1. 10 plus 20 plus 60 times 10 minus 675 is equal to F1. 900, oops, not you. 900, 675 is 225. And that's it. And so that's the general layout of a torque bar problem. That's the general layout of the test. Yes, in the back. I don't have to solve for R2 because A, it was never asked for, and B, it was never asked for. Do you want me to solve for it? You know what? I think it's kind of irrelevant because I think that if it's a constant R, it's more, you're more interested in the proportions than the specific value of R. Yes? My masses came from the fact that I gave them. So that's where. That's it. Office hours until noon, and then you're free to come to the 4 o'clock lecture. See you later. This will be online shortly.